Now we're going to look at counting atoms and molecules by their mass. So the masses of elements on the periodic table increase as you go down. Hydrogen starts with about 1, carbon you're to about 12. As you go down, they just keep getting bigger. It helps to know how these masses relate to atomic mass units, the mole, and grams. When you understand how to use them, then you're able to do a lot of calculations about what you're doing in the laboratory. So we're going to cover those concepts, and then we're going to relate them to chemical equations. How do you use it once you understand it? Here is a periodic table, and you'll notice the mass numbers are located below each symbol. And those mass numbers are in atomic mass units, which they relate back to the mass of carbon. And they give carbon 12, the isotope carbon 12, a mass of 12, and then they figure out the masses of everything based off of that. They did that because, to begin with, the only thing they could figure out mass-wise was proportions, because atoms were so tiny that they couldn't figure out individually what was going on for each element. And so instead, they did it by proportions. Well, in the laboratory, that isn't very useful, so we have to come up with something more useful than the mass of one atom. So AMU stands for atomic mass units. And if you look at the periodic table, hydrogen has 1.0079 AMU, carbon has 12.011 AMU, and that isn't strictly 12 because there are other isotopes of carbon-13 that are averaged in there that are bringing that number up. And you have potassium, 39.098 AMU. So just be sure you can identify those and know where I'm getting these numbers from. So to find out the molecular mass in AMU, you would end up adding up the atomic masses of the atoms involved. So salt, table salt, is NaCl, sodium chloride. If we add up the mass for 1 sodium and 1 chlorine, that will give us the AMU for 1 NaCl, 1 molecule of table salt. If I have carbon tetrafluoride, I would do something very similar. I would take the mass for 1 carbon, and then I'd take the mass for fluorine and I'd multiply it by 4 because there's 4 atoms there. And I'd add all those up and it would give me the AMU for carbon tetrafluoride. So here's the math here. There's the sodium, the chlorine. We add them together. We get 58.443 AMU. For our carbon tetrafluoride, we take the amount of our carbon, but we only have to multiply that by 1. If we take our fluorine, we have to multiply by 4. So we're going to have 12.011 plus 75.992. That gives us a mass of 88.003 AMU for carbon tetrafluoride. Now, if I were to ask you to volunteer and ask you to come up and measure AMU with a scale like you'd find in a laboratory, you wouldn't be able to even see what you have in AMU on your scale. It's a molecule. A molecule is so tiny you can't see it with your eye. So AMU are really fascinating. It's a great fact, but it's not very useful when you get to the lab because you want to work with quantities you can see, which are going to be much, much bigger than 1 molecule. So we need a conversion that would take that small mass and convert it to grams, because that's what we weigh with in a laboratory. A gram is about the weight of a paper clip, and those scales in a laboratory measure in grams. So as it turns out, if I were to take 6.022 times 10 to the 23rd AMUs, take the little tiny weights of AMU and do 6.022 times 10 to the 23rd of them, so this is a really big number, put those little weights on my scale, the scale would give me a mass of exactly 1 gram. So there's our conversion. If I know my AMUs, if I take 6.022 times 10 to the 23rd molecules, it's going to translate into grams. So they call this Avogadro's number, and it's a large number. Instead of using it, we talk about things coming in packets of 6.022 times 10 to the 23rd because we'd be writing that number out a lot if we used it in full. So it's kind of like something that we do in everyday life, which is eggs. When you go to the store, you don't ask them for a single egg generally. You ask for a half dozen, which would be 6, or a dozen, which is 12, or a dozen and a half, which is 18. Sometimes 2 dozen, 24. You don't ask for those individual eggs. It's not really practical to stick an egg in your cart. It would be crushed. And usually you're using more than one. So it's the same sort of concept. We're going to talk in dozens of molecules, only we're going to talk about a whole Avogadro's number of those molecules. And instead of calling it an Avogadro's number, they call it a mole. M-O-L-E, and the abbreviation is M-O-L. So just as 12 is 1 dozen, 6.022 times 10 to the 23rd is also called 1 mole. So we talk about the moles that we work with in the lab, just like we talk about the dozens that we work with when we're working with eggs. So this is just a number of something. It's a counted number. It's not a weight, but when we count that number, then the AMU that we calculate is equal to the grams per 1 mole. So if I have 1.56 times 10 to the 24th molecules of water, how many moles of that water would I have? Well, we'd take this number and we divide it by Avogadro's number, and we find out that we have 2.5 moles of water there. It's 2.5 times the quantity of Avogadro's number. So how big is a mole? I mean, this number is something that we don't work with in everyday life. So if I were to take unpopped popcorn kernels and spread them across the United States evenly, and it was 1 mole of them, it would result in the country being covered 9 miles deep in popcorn kernels. So what does this mean? It means atoms are really tiny. And in the lab, we're always working with many, many atoms just to get to dimensions that we can see and handle in a laboratory. We can determine the mass of atoms in grams if we assume that we're working with 1 mole of them. So 1 atom of helium is 4.026 AMU. And if we took 6.022 times 10 to the 23rd atoms of helium, then it would weigh, and put them all together and took their mass, we'd get 4.0026 grams of helium. So you see how that beautifully transitions into something we could use in a lab. The atomic mass is also the grams of 1 mole of the atoms would weigh. So we just take what we have on the periodic table for AMU, and it's also grams over moles, grams per 1 mole. So here we have some elements. If you look at your periodic table, go ahead and look up the slide a little bit. There's silicon there. It's 28.086 grams per mole, calcium 40.078 grams per mole, phosphorus 30.974 grams per mole, and iodine 126.90 grams per mole. You'll notice these are just the atomic masses on the periodic table, but we've changed the units on them to grams per mole so that we're working with something we'd actually work with in the lab measurement-wise. The same principle works for calculating the mass of something bigger than atoms when we're working with molecules. So what grams per mole would you assign to water? We would take 2 hydrogen, 2 of the mass of hydrogen and 1 of the mass of oxygen, and we get 18.015 when we add that together, grams per mole. And so the molar weight, sometimes called the molecular mass of water, is going to be about 18 grams per mole. So when we use these grams per mole amounts, they're used as conversions. We can convert between moles and grams. And that can be a little disconcerting to begin with because you're unfamiliar with the term mole and using that as a unit. But it's basically counted numbers of atoms just done on a large scale. And grams you're probably a little more comfortable with. So let's say we had a 1/4 mole of aluminum metal. How many grams would we want to measure out if we wanted that amount of aluminum? So we could take our 0.25 moles, that's what we want. We use the conversion from the periodic table that 26.982 grams of aluminum is equal to 1 mole of aluminum. And our moles would cancel because we've got it in our numerator to begin with and in our denominator in our conversion, so they cancel mathematically. And we multiply our numbers together and we divide, but you divide by 1 and you get the same thing. And you get 6.75 grams of aluminum. That's how much I would measure out to get a quarter mole of aluminum. It can also be flipped over and used to convert grams to moles. So let's say you measure out 23.4 grams of lithium bromide. How many moles of lithium bromide do you have in that amount? So we would take our starting information, which is we started with 23.4 grams of lithium bromide, and then we'd use the conversion of the molecular weight of lithium bromide. So I've added the mass of lithium and the mass of bromine together here, and it's just a 1-to-1 because there are no subscripts other than blank there, which means there's one of each. And this time I'll put the gram amount on the bottom and 1 mole on the top. Notice I now have grams in my numerator and my denominator, so they're going to cancel, and the units that are left are moles. So we get, once we do the math, 0.269 moles of lithium bromide. So we can go between grams and moles of a particular element or molecule, and then the next question would be, if we're doing this with a chemical equation, how does that work? So the coefficients in a chemical equation are mole-to-mole conversions. So here we have 2 nitrogen dioxides. They're a gas and they go to form dinitrogen tetroxide, 1 mole of those. So we would read 2 moles goes to 1 mole. So if I had 6 moles of nitrogen dioxide and it all reacted to make dinitrogen tetroxide, I could ask, well, how many moles of dinitrogen tetroxide would I get? So I take my starting information, which is I have 6 moles of nitrogen dioxide, and then I can use the coefficients as a conversion. For every 1 N2O4, I have 2 N2O2. Notice those are just the coefficients from my balanced chemical equation. I put the one I want as my final answer on top. The one I'm trying to cancel is the one on the bottom. And the ending thing that I'll get is that I would get 3 moles of dinitrogen tetroxide out of 6 moles of nitrogen dioxide. So it will cancel out using those coefficients. It'll provide you with a way to convert from one molecule in a chemical equation to a quantity of another molecule in the chemical equation. But it only works from moles, so make sure that you're always starting with moles or that you convert to moles before you use the coefficients to go from some substance to another substance. If they're in grams, because things weigh different amounts, like if I took the weight of a baby and the weight of an adult and just gave you, well, we have this mass of babies and this mass of adults, that the numbers wouldn't convert entirely. If I said, oh, I want 2 adults to each child, you wouldn't be able to tell from the masses how that's going to convert. I need to know how much weight a baby weighs and how much weight an adult weighs and convert them to people in order to see that conversion. So it's that same sort of thing.